Hi guys, welcome to the video tutorial for electric cells. This is part 2 and it looks like we've got quite a few learning objectives to cover today, so let's dive right into this. First learning objective is fairly straightforward. We want to define what internal resistance is. So the definition you can see in black here is the resistance, it is the internal resistance of a cell, is the electrical resistance of the cell itself. And this is associated with electrical chemical reactions. So as the cell is producing its voltage, when the current is being drawn, there is going to be an electrical chemical reaction, and inside of that there's going to be a little bit of resistance. And we're going to see a little bit more on this later, but the variable for resistance is little r because there's less of it. So this is quite similar to for the HL students, where we've been talking about like big M for a large mass and little m for little mass, as well as big Q and little q. So you can see a lot of similarities in how they like to do this in physics, where if something is of a larger quantity, they'll use the capital letter. And if something is of a smaller quantity or amount, then we use the smaller letter, okay? So internal resistance is usually a very small number in comparison to other things, okay? So internal resistance. Okay, next up, we're going to describe a circuit to find the internal resistance of a cell. So essentially, we just want to know, what does the circuit actually look like, okay? So what we're seeing here, this particular part right here, this is sort of the cell itself, okay? And normally, I've got a little diagram down here, is our battery, okay, our terminals of our battery, so our negative and our positive ends are the A and B ends. Okay, so that's why this diagram looks the way it is. Okay, so we were looking at what does that look like in terms of the circuit diagram. Okay, so next up we're going to get into some calculations. So we want to be able to calculate the internal resistance and give the EMF of a cell from a graph of voltage or potential difference against current. Now we're going to look at the graph part of this a little bit later, but we are going to get into the concepts of electromotive force, or EMF, and internal resistance, okay? So internal resistance can be calculated as power equals to I squared times little r. Now this is not a new formula, okay? You will remember that we had P equals to IV, right? And then we had that lesson where we substituted, again, using Ohm's law, V equals to IR, okay? And then we have a different derivation of I squared R, right? And so all we're really doing is, this is, we've already talked about, we've seen this form, or this formula form for power already, okay? And all we're really doing is we're replacing a big resistance with a little resistance, okay? So there's nothing really new in this formula, okay? But in terms of what it represents, P is the power dissipated in a cell, measured in watts. I is the current produced by the cell, measured in amps. And R is the internal resistance of the cell, measured in ohms, okay? So obviously we can rearrange this. This is in the data booklet, but it's not in the chapter 5.3. I already mentioned that this is part of the power formula, okay? So another interesting thing to note is that the internal resistance will change with temperature. And this is because internal resistance, we already mentioned this earlier as part of the definition, is that it's associated with electrochemical changes. And so what I want you to do right now is, here we have a sample of some different values of resistance. Okay, so we have resistance here, and we have temperature here. So I want you to look at this data, and I want you to now think about, what can you say about, what is the relationship between temperature and resistance? So pause the video, think about that, okay? All right, so hopefully you've had a chance to think about it. You've maybe said it out loud, or maybe you've even made a note on it. And so the relationship here is that as the temperature drops, the resistance increases. Okay, so there is, you can call this an inverse relationship, right? As the temperature goes up, the resistance goes down. Okay, so that is roughly the conclusion that we can draw from this. Now, there's a pretty cool video that if you guys have lived in cold climates like Canada, where it snows and it reaches minus temperatures for long durations of the winter, a lot of the times you'll see that cars have to be plugged in, and so I've got a hyperlink in Google Classroom. You can YouTube it. It's called Battery Blanket. Okay, so go ahead and do a search for that. I'll probably try to link this up in the comment section for you guys. Okay, learning objective. Number 4, derive and use the formula V equals to E, that's EMF, so this is EMF actually, minus I times little r. Now, don't really let yourself be fooled by this, okay? So I'm going to just show you how this formula was derived. And it's actually just potential differences, okay? So here we have a sample of that diagram. So we're going to get into this in just a moment, but EMF is actually it's the undisturbed, it's sort of the full potential or full electric potential of a cell, okay, without the internal resistance. What we actually use when we use our battery, it's already taken into account that there is some internal resistance there already. Okay, so it's even higher than what a cell would be. So if a cell, like a AA battery, has 1.5 volts, the EMF should be, in theory, even higher than that, so maybe 1.6 volts. Okay. All right, so let's get into the derivation of this formula above. Okay, so we're going to derive that right here. So we start with E, okay, which is the voltage of the battery without internal resistance. Okay, I've already mentioned that. I'm going to use a different color to highlight this. Voltage of the battery with resistance is what we call the voltage between A and B. Okay, so that's sort of the whole battery, VAB, right, A and B. Right, so we sort of imagine the whole battery. Voltage at terminals A and B. And then V is the voltage of the circuit, okay? So this is what, so it's actually all just voltage is voltage is voltage, okay? So the total voltage, you can say, is the addition of the battery voltage. This is with internal resistance calculated, and that of the circuit. And so a little bit more rearrangement using Ohm's law, V equals to IR, or V equals to I little r, okay? So it's all still resistance, guys, okay? It's just more or less of it, okay? And this is actually the formula that you will see in your data booklet, all right? So that's how we derive that. So both of these versions are more or less the same. I mean, this is the more simplified version, I guess. Okay. So what exactly was EMF? I've briefly mentioned that already. So in terms of the word definition for EMF, the electromotive force, and it's not actually a force, which is why I wrote it, and then we call it the electromotive force, but don't think of it as a force, which is why I have a red line through the word force. Okay, but it was an old terminology that kind of stuck with physics. Again, it adds more to the confusion, but it's a historical sort of name convention. Is a total electric potential energy supplied to a circuit, okay? So you could say total or maximum, okay? But it's, it is what the cell could produce without the internal resistance. Mentioned that more than a few times already. It is really a variation of potential difference and not a force. Okay, so I've already mentioned that already. Okay, it's not a force. Make sure you get that clear right now. And the unit, wow, my T looks like an F. The unit for EMF is volts, or voltage, okay? And so, yeah, that's what it is, okay? And I've got here that EMF is the potential difference with no current flow. We're going to see this in the graphing section. So We'll get back to that a little bit later, all right? Again, just a quick little diagram to show you that EMF, V, volts, okay? So these three things look quite similar, and in many ways we might sort of confuse and mix these guys up in our brains. And sometimes we can kind of use them interchangeably, but let's just clear that up right now, okay? They are all voltage, you might say, okay? But as mentioned, EMF definition, total or maximum voltage without internal resistance. V is the more common everyday term that we use, but we use V as the quantity variable, but we call it the potential difference. In everyday terminology, people would call it the voltage, like 1.5 volts of a AA battery, okay? And volts is the unit of measurement, okay? So be careful that you don't confuse these things, and that even though they are all talking about potential differences on different things in different ways, you have to make sure you understand and distinguish those differences for yourself. Okay, now the other thing that we needed to talk about was the formula, E equals to W over Q. And again, there's nothing new here. It's just writing V as EMF instead, okay? So the electromotive force of the battery is the work done per unit charge, and we can describe W, as the amount of energy to move Q charges around or through a circuit, where Q is the total number of charges that are moved. So W energy, Q total number of charges being moved, okay? And so let's maybe get into some calculations from a little bit earlier, because we didn't really get into any calculations. So this is more in line with our other learning objective, but it's sort of all combined together. So what is the internal resistance in the following circuit given the information below? So we have the EMF is 12 volts, and then the terminals of the battery is 10 volts. So there's a few different ways that we can solve this. We can solve this by taking the total voltage, total current, and total resistance. So we can apply Ohm's law to the absolute total or maximum of everything, okay? So the absolute total of the entire circuit is 12 volts, and we have 2 amps, and then so the total resistance would include the internal resistance. So it's everything external plus that little r all together, right? So RT, you can actually see the sample here, is the 2 resistors plus the internal resistance. And so if we solve for that, RT, so 12 divided by 2 is going to be 6 ohms. And then so now we can resubstitute that back over here. We have 6 ohms of total resistance minus 2 equals 2.5 plus R, okay? So this is pretty straightforward. 6 ohms, simplify that to 5 ohms. And so we know that there's 1 ohm left over in the internal resistance, okay? So that's one way that we can solve this. Another way we can solve this is to use sort of the formulas that was given to us a little bit earlier, okay? So the EMF is 12 volts. The voltage at the terminals is 10 volts, okay? And therefore the voltage supplied that's used up by the battery is going to be what's left over. So we call this V circuit. Okay, so essentially when we subtract that, we've got 2 volts, and that's the voltage of the circuit, okay, or the voltage of the battery, I guess is maybe a better word. So anyways, we have 2 volts that's being used up by the battery. The current, remember that current is constant in series, so this 2 amps goes through that 2 ohm resistor as well, okay? So essentially this also gives us the same thing, that the resistance, the internal resistance is 1 ohm only. So I might have to change that word up instead of circuit, okay? But it's referring to the battery itself. Okay, lastly, our last learning objective, we're sort of going back to the third one, is to calculate the internal resistance and give the EMF of a cell from a graph of voltage against current. Okay, and that's exactly what we've got here. Sorry, I didn't label this, but that's in amps. So this is current in amps, and voltage, potential difference in volts. And so here we have a graph here, and there's a few pieces of information that you need to be able to read from the graph, okay? So aside from being able to calculate the internal resistance, which is actually just the slope, we'll talk about that in a second. So first off, we can observe that at 9 volts, there's no current. This is the EMF value, 9 volts, okay? This was defined a little bit earlier. Right, recall that E is no current. Go back up and check on that. Let me see if I can maybe go up and show you guys where that was, okay? This part right here, right? So that's taking that, but it's applying it to the graph. Okay, now the lowest point in the graph, so where it actually touches the highest, this is the maximum current that's going to be supplied, okay? And so as a result of that, we're going to look at some calculations in just a moment. But the slope of this line is essentially -1, right? Each time it drops 1 at a time, so it's -1 slope. And so this sounds a little bit odd, but the negative of the slope, so when you flip it then, you get the internal resistance, right? Because the slope is -1. When you take the negative of it, so you have a double negative, it flips it back to a positive. So the internal resistance ends up being 1 ohm. We can read that directly from the slope of the graph. In terms of the calculation, we can also do that as well. So this is actually the same calculation that we did about a few minutes ago. So the EMF is 9 volts. The voltage at the terminal is actually where the maximum current is supplied. So this is 5 volts, okay? And then, so what we have is we have what's left over. The circuit or the battery itself is eating up or using 4 volts. Wow, that's a lot actually. So when we simplify the math, we have 4 volts being supplied. So the V of the circuit, or the internal, the battery itself. So again, we can substitute that 4 volts being used up by the battery. It's drawing 4 amps, right? Remember, whoops, probably shouldn't. I'm just going to do that inside, okay? So the maximum current is 4 amps, okay? So 4 amps, everything is the current, no, not everything. Current is consistent in series, okay? And so when we do the division, we also get 1 ohm as well, okay? And so I quite like this unit in the sense, these calculations, in the sense that you can solve for things in multiple ways, and that also allows you to check your answers as well. Okay, guys, thanks for watching, and we will be back. That's it for 5.3, and we'll be back in for 5.4. Okay, check the comments below. I'll have that blanket battery video linked up for you guys. See you later.